Hello everyone and welcome back to the channel. In this video, we are analyzing a Cobalt Strike Loader. We start off with the analysis of the loader binary itself. From there, we extract the encoded shellcode. We then move on to decode that shellcode and do further analysis of the shellcode. During the analysis of the shellcode, we learn how hash API hash resolution works, and we are also going to discuss how the shellcode uses its own PEB to access the kernel32.dll module, and then from there it dynamically resolves the APIs. This is going to be a fun one, and I hope you are able to follow along with me on this journey. With that, let's get started. So here I'm in my virtual machine. I have this folder open in front of me, which has the sample and a script. We are going to open up the sample in Hydra Pro. So let me open up Hydra Pro and load the sample in. Press OK and select the sample. Everything default is fine. Press OK over here and we are good to go. All right, the first thing that I do usually when I'm analyzing a sample in Hydra Pro is that I produce a file just to make sure that the C file is produced. And what this does is it effectively decompiles the whole code. So there is no just-in-time decompiling, and so we don't have to figure out whether this code might be correct or incorrect. So I'll just save it here and we can see that it has decompiled the whole code. Okay, now let me press F5 and we can see the decompilation of main. I can put this here on the side, and I can also say that I want this to be synchronized with the pseudocode. All right, so we have two functions here. Let me just give myself some space. We have two functions here. The first function, if not a d word and there is nothing in d word, then this function occurs. And if we go inside this function and further go inside this function, we see one exit v1. So we're not interested in this function. So let's go to our next function. So escape from here and escape from here as well. And let's go to our main from here and see what's next. So main and F5 once more, and let's go to our second function. In this second function, we see something interesting. We see that a buffer is being set up with some values. These values indicate that this is a name of a named pipe, and this is synonymous to what we see in usual Cobalt Strike beacons. All right, so we have this being set up in the buffer, and we also have a thread being created with this function. So let us open this function. Here we see that there is some kind of a byte data being passed to this function. If we see this, we can see that this is some raw data. And if you go inside this function, we see that this data, let's look at that, the buffer. If you look at this data over here, we can see that this data is being written to a named pipe, and after that the handle is being closed. So let's go back and let's see what is happening after this. So we have another function over here, and in this function we have this function being called, and in this function we see that there is some data being read from the name pipe. All right, this is the same name pipe where the values had been written previously. So let's go back. There is another function which is here, and if we go inside this, we are seeing a virtual alloc, and the virtual alloc is for 3000 hex, and we have a while loop, and this while loop is running until the size. If we go back and look at the size here, the size is 353 hex. If we see that in decimal, it is 851. Okay, so let's go here and let's see what is going on here. So there is a while loop, and this is our index. So let me just rename this, rename L bar, and let's just say loop I underscore, oh sorry, I loop index. Okay, so integer loop index, while integer loop index is less than the size. So although we allocated 3000 hex bytes over here, the size is actually 851. So while loop is being run here and we are assigning some data from this A1 is our buffer. So v0 is being fetched from here, from this function where we have read data from the name pipe, and v0, let's rename this when we go inside this function a1 to let's just say that this is a byte array. Okay, and this is going to be byte pointer. Okay, so we have this byte array over here, and in this we are looping over this byte array, and every byte is being XORed with this A3. And let's see what is this A3. If we go back here, A3 is another chunk of data, and this time we see that this data is 1 2 3 4 bytes. Okay, so if we go here and we can say that this is our key, because we can see that this is being XORed over here, and the type of this is byte pointer. Okay, now this becomes quite clear. If we want to change this as well, we can change this as well, and we can say that this is a byte pointer v3. Okay, and so this becomes really clear, right? So v3 is being assigned the value which is coming out of the XOR operation between the original data with the key. Okay, now let's go back. We have to extract both of these things, the original data and the key, to get us, what do we get? What we get is v3, which is some sort of decoded data, and this decoded data is being sent to this function, and from here we see that there is some get proc address, get module handle, and after that we see something that v5 has been assigned this decoded data. We are using this to start a new thread. So let me rename this ptr decoded data. So we can see that a thread is being created with this decoded data. So this looks like shellcode. All right, so let's see how we can extract the shellcode, and we'll have to obviously decode it as well. So let's keep on going back a bit, and we can see that there is this function being called, and we have, this is the data. We know that the size of this data is 851, and the location is in the data segment 403014. Okay, so let's go back and let's see where the key is coming from. The key is being used in this function, and it is coming from data 403008, and this is quite simple: 0e d595 and c0. All right, so I've created a simple script. In that simple script, we are going to perform essentially the same operation that is being performed here. We are going to XOR the original byte array with the key, and we are going to get this decoded shellcode. So let's see that in action. We see that this is the script. In this, we have the file name, we have the payload virtual address, which is the the encoded bytes or the encrypted bytes, which starts at 403014. Then we have the size of the payload, which is 851 bytes, and then we have the key over here. If we go to analyze the code, we see that we are using the PE module or P file module of Python and giving it the sample path, which is actually a PE file. We can extract the image base, the address of the entry point, etc., etc., and we can also convert anything which is in an RVA to a file offset, and from there we are going to extract the data. So we see here that we are getting the data, and we have the virtual address minus the image base. We are actually extracting the data from the PE file directly using the PE module, but we could also get it directly from directly through reading the file from the file offset. All right, after that we are using the XOR decrypt function. If you go to this function, we are sending it the original data, and we are sending it the key, and we are then going to XOR the encoded data with the key to get our decrypted data. Okay, so let me execute the script. By the way, I will share all of this, the sample hash and the script on the GitHub, and I will share the link to the repo in the description of the video. All right, so let's play this, and once we run this, we see a few things. Okay, number one is that we have a loading PE file with base, image base, entry point, number of sections, whatever. And then we are getting 855 bytes of encrypted payload and decrypting it with the XOR key, this. Okay, the decrypted payload is being saved here, decrypted shellcode simple.bin, and we see that it starts from FC E88960 whatever. So this is basically our decrypted shellcode. All right, now let's save this and let's go and analyze this shellcode, because now the story is going to continue from the execution of the shellcode. From here, we will continue our analysis of the shellcode in IDA-Pro as well. So let me open up IDA-Pro, press OK, new. Let me load up the shellcode, press OK here again. This shellcode is 32-bit. Okay, and press C over here. We see that the shellcode always starts execution from 0. So we have our clear directional flag, then we have the call to a function sub 8f. We also see something interesting over here. We can see that this 30, 0c and 14h, these are indicators that the shellcode is doing some dynamic API resolution, and it is using the address of the kernel 32 module, which is loaded in every executable, to basically resolve the functions for a load library and get proc address or something similar. And from there, it will continue the execution by resolving the APIs dynamically. Okay, before we continue on with our code analysis, in order to better understand this and to mark this IDB properly, we have to add the Windows type library. So if you go here, view, open subviews, type libraries, add or load a type library here, and select ND API. ND API, press OK. From here, we have to add some local types as well. I'm going to quickly add those types, and we will continue this video after I have added those. So go to struct, import, over here, control F underscore tab. Remember, we have to add the underscore tab structure. Then here press the insert key again, import structure, control F underscore fib, add this as well. And another one is going to be image toss header. So f image toss header. Next up, we have to add the image nt header. We want to focus on the 32-bit version of this. Another one is going to be the image file header, which is Control F, image file. Press OK. All right. Next, we can go to our IDA view and we can continue our analysis. Let me just save this database. Let's go to our call to this function sub8f. And here we see a couple of interesting things. We see these long hex numbers here, and there can be two things which I understand from these. Either these are strings or either these are hashes. And we'll see how I work through those. So I usually right click on this. So right click on this and I see something which makes sense to me in terms of a string. So I can see 10 here. So let me add that. And if I add this one as well, now this makes perfect sense. Win inet. Okay, so it's clear that this win inet library is being resolved over here. Next up, let's see what this is. This looks like a hash, so I'm going to run hash db hunt algorithm. And it is saying that it could be either metasploit or sh1 add. I'm going to use metasploit, and from here I will say hash db lookup. It says that this is the load library A. I'm going to import this. Next up, let's look for this one, hash db lookup. Internet open A. If the API does not come here automatically, just press the M key and we should see the API here. Now, if we move forward, we can see that this is a jump to location 15E. Let's take that jump. And then we have another jump to this one. Okay. Now, this is interesting. We can see a couple of things here. Number one is that we see that there is some sort of URL over here. Let me undefine this code here as well. And we can see this CS45. So this is one string. So let me just convert this to a string. And the way to convert this to a string is edit strings, and we can see this A here. So I will press A directly over here and we see the string being created here. And now we saw that that there was a jump to this part of the code, but we can see that this is currently undefined. So let us convert this to code as well. We have converted this to code, but the URL that we had here is gone. So I have to convert this to code, but I have to undefine this. Okay, so we have our URL here again. Press A to convert this to a URL. These are some small tricks in IDA Pro which you will understand as you play around and use this. Okay, so now if you go back, we will understand the code a bit better. So we have a call to or a jump to location 15E, and from here we have a jump to location 32C, and we have a call to location BA. Okay, when the call is made, the next instruction or the next address, so after this the next address is 331. This address ends up on the stack. Now imagine this is the on top of the stack, and then let's go back and see what happens after this jump. So after this jump, pop EBX is there. So whatever was on top of the stack is now in EBX. Okay, and if we highlight EBX, we are seeing that there is a push EBX. Now this URL is going to be communicated or is going to be used for communication, so this has to be some sort of an API call. So let's do a hash db lookup here, and we can see appropriately that we have an internet connect a API call. Again, this is not automatically resolved, so I will press M here. Okay, and then we have we move on with a similar understanding. So location 163, it's going again to D7, and from here it continues on with the execution. If we go back to our data section, we can see some more interesting strings here as well. So if I press A here, convert this to string, we can see that this is a user agent string here being used. And obviously if we go down further, we will see our URL. Okay, so let's go back and let's resolve the other APIs as well. This is not an API. This is most probably some parameters being passed for an API call. So this would be an API call, HTTP open request A, and as I understood, this looks like the values that are passed to the HTTP open request A. Next up, we have another API call. This is internet set option A. We have some options being set for this API. Next up, we have another API called hash db lookup. We have HTTP send request A. Another one, which is get lost error. Another one, okay, it needs a bit more time. Another one, get desktop window. Another one is internet error dialog. And we see the code reaching its conclusion over here. So let us review the API calls one more time. So initially it is using load library A to load the WinINet library. From there it calls internet open EA, internet connect A. From here HTTP open request A, internet set option A, HTTP send request, get desktop window, internet error dialog, and so on and so forth. We will see some more things happening here. Let's go back to our start of our code. We can see here that we had the API resolution happening over here. I am basically looking for some code where it is reading a file or downloading a file. Let me just see if there is any other code we can find. Okay, so this here we have another piece of code which is which might be doing something. And if we look at the XLFs to this, okay, so there is a call to this place. Let's see if we can resolve these APIs as well, because there is one call that is missing, and this call should be read file or something like that. Virtual alloc. Okay, press M, switch just to virtual alloc, and let's see hash db lookup over here as well. Internet read file. Okay, and around here there should be something else as well. All right, so this is where I was getting confused. I was missing a jump here, and I've seen that there is a jump here as well. So location 163, if I go here, then there is a call to location D7, and this code is a bit suspicious. And when there is a call like this, the next address should be pushed onto the stack. And if we undefine this code here and convert this to a string, we can see that there is a part of a URL being used here, which is a WZ9R. if we go to this, the call to this, in fact, let me go up here. (15E). Where is this call? Jump. Okay, so this one. If we see here, there is a jump to location 163 and a URL was being added on the stack, and from here that value is being popped into EBX, and we will see that this value is being pushed here into EBX as well. So HTTP open request is basically opening a request to our URL, but then it is appending a certain value to the URL as well, which is the slash something something. Anyways, so after this there is an HTTP send request here, HTTP error dialog, and from there is further execution when we have the virtual alloc and we have the internet read file here as well. Okay, and we've already seen this part of the code. Okay, now let's go back to the start of our code and let's see how the dynamic API resolution takes place. We are going to mark this area. For now, I will just mark this area and leave it as it is. What you can do is try to explore this using MSDN, and you should be able to understand how this API resolution is being used here. So structure offset, we are looking for the tab.process environment block. So from here it gets access to the process environment block, and if we move on, this is peb.something. I think it's this one, peb loader in load order module .flink. So it's this one, and from here if we go to 14, it should be I think this should be the loader. I don't know why I got this. Should be the LDR, peb.ldr, sorry, and from here 14, it should be the LDR.flink. This is fine, and from here the next one would be the LDR table dot it should be the buffer, this one, and this one has to be the maximum length. So what is happening is that it is using the shellcode is using the tab to get access to the peb process environment block, and from here the peb, it is accessing the loader data. From there from the loader data, it is basically accessing the in-memory order module list. So in the modules that have been loaded, which are in the form of a list, which is a doubly linked list, and it is asking for the first link. From there, it is going to traverse through this list and accessing the buffer, which is going to be the full DLL name and the length of the full DLL name by getting the maximum length. From here, it is going to traverse through it and it's going to look for the kernel 32 module. Okay, after this code has been marked, it should be fairly easy to continue with the analysis. And we've also looked at the analysis of the shellcode on how it is doing API resolution and how it is connecting to a secondary link to download the secondary payload as well. So I think that brings us to the end of this video. Thank you very much for your time.